Okay, in this lecture, we're going to talk a bit more about weak solutions of nonlinear conservation laws and the idea that there are sometimes non-unique weak solutions and we need to pick out the physically reasonable one. And so we'll talk about just kind of review some things about weak solutions in conservation form, but that will lead into a discussion of entropy conditions and entropy functions as a way to impose admissibility criteria. And then we'll look at the weak form of the entropy condition and how that relates to the vanishing viscosity solution and how you can show that satisfying a certain kind of entropy condition guarantees that you're converging to the right vanishing viscosity solution. So just to recall, we say that Q is a weak solution of the conservation law if it satisfies this integrated form, which we've used to derive the finite volume methods, for example, or equivalently, if we multiply by a smooth test function and integrate over a rectangle and integrate by parts, we can derive this weak form, which we'll be using later on when we look at convergence proofs as well. And the entropy condition we'll look at in similar ways. A function that's piecewise smooth but just has jump discontinuities is known to be a weak solution if the PDE in the strong form up at the top here is satisfied where Q is smooth, but also if the jump discontinuities satisfy the Rankine-Hugoniot conditions that come from looking at the integrated form. But as we've seen, the weak solution might not be unique, and there can be situations where we need to pick out the correct one, the physical one often being the one that's determined by adding in some small viscosity and looking at the limit as that viscosity vanishes. But before diving into that, let me recall that a method is said to be in conservation form if we can look at it this way as updating a cell average in each time step by taking the previous cell average and modifying it by a difference in numerical fluxes at the two edges of the cells, which come from approximating the integral in time of the flux at the edges of the cells coming out of the integral form. And the reason that it's nice to have things in conservation form is that then we're mimicking the conservative property of the differential equation. In particular, if we sum up over the entire grid qi at n plus 1 times delta x, then we get, just from summing this formula at the top here, we get the same sum as we had before, plus we have the sum of all these differences of fluxes, and they all cancel out except at the boundaries. Wherever our boundaries are, I've just denoted those by f plus infinity and f minus infinity, but they might be at some finite limits. And then the fluxes at the boundary would determine how the integral of q behaves in the interior, but this says the numerical method is preserving that. And as a special case, we've seen that if you have an isolated shock, just a discontinuity that should be propagating as a shock wave, for example, in Berger's equation perhaps, then by sort of applying this over any interval x1, x2 that includes that shock wave, what you can see is that from this discrete conservation form, the integral, or the sum of the q's, has to be increasing at exactly the right rate, which means that this isolated shock must be traveling at the right speed. It might get smeared out by your numerical method. It might become oscillatory if you're using a dispersive method, but at least the average speed is correct. It's got the correct total mass. So if we look at a nonlinear equation like Berger's equation, then remember we can also write it in quasi-linear form, and if the solution is smooth, then those are equivalent, but not for shock waves. And I think I showed this example before, but if we just look at a couple of different natural discretizations that are sort of both generalizations of the upwind method for advection to the Berger's equation case, if we assume that u is positive so that everything is propagating to the right, then one way we might generalize this is in this conservative form, where we're updating the cell average by taking the flux at the left edge and the flux at the right edge rather, and subtracting off the flux at the left edge of the cell, and then using the fact that u is greater than 0, we know that those fluxes are coming from the adjacent cell to the left of each of those interfaces. And so this is using the flux from the conservative form and doing a flux differencing in conservation form, and that's a conservative method that guarantees that shocks will propagate at the correct speed. On the other hand, if we started with the quasi-linear equation that sort of looks like an advection equation, but where the advection velocity is the same as the solution, and discretize it by uin, the advection velocity, times the jump in u in the upwind direction, that would be a natural generalization of the advection method. Then for smooth solutions, that would work perfectly well. Either one of these is first order accurate, and they'd probably give very similar solutions. But if you apply it to a problem that has a isolated shock wave moving along, then the conservative method gives a nice looking solution, whereas the quasi-linear upwind method gives a slightly more smeared out solution, but the key fact is that the shock is in totally the wrong location. So is it reasonable to expect that we would get shocks in the wrong location just because we're using a slightly different variant of the equation? Well, yes, it is, because if we think about it, if you take two different conservation laws that have the same quasi-linear form but different jump conditions, then they would have different weak solutions. They would have shocks that propagate at different speeds, even though they might have the same quasi-linear form and exactly the same sets of smooth solutions. So here I've taken Berger's equation again, but I've also written down another equation, a conservation law, but where u squared is the conserved quantity, and the flux function is taken to be 2/3 u cubed. So that's a conservation law also, but it's conserving u squared. And if you work out the quasi-linear form for the second equation, if we differentiate this through, we get 2u ut, plus we'll get, when we differentiate the other equation, we'll get 2u u squared times ux, and if we cancel out the two u's, we end up with this equation, which is exactly the same as the quasi-linear form of Berger's equation. So these two conservation laws are conserving different things, but they both have the same quasi-linear form and would give the same smooth solutions. However, if we look at the Rankine-Hugoniot condition that tells us what speed a shock goes at, we can easily compute that they have different shock speeds. So if we have a weak solution, they will be quite different. So here's the calculation of the Rankine-Hugoniot condition. For Berger's equation, as we've seen before, the shock speed is the jump in flux divided by the jump in u, which you can simplify to just being the average of u left and u right. On the other hand, for this other conservation law, it's the jump in flux, so it's the jump in 2/3 u cubed divided by the jump in the conserved quantity, which is u squared. So that's the denominator here. And we get an expression that looks quite different. And in fact, the speed on the bottom is always greater than the speed given by Berger's equation. Take, for example, u left equals 1 and ur equals 0, then the two shock speeds are just 1/2 and 2/3 in that case, for example. So if these two different equations that both have the same quasi-linear form can give different speed shocks, then it's not surprising that if we solve the quasi-linear equation, it's not clear what we're going to converge to, whether we'll converge to a solution of the top equation, Berger's equation, that we're trying to solve, or whether we'll converge to a solution of this other equation, which has exactly the same quasi-linear form. So that's why using the quasi-linear form for our numerical discretization is a bad idea. We don't know which conservation law we're actually modeling in the case of shock waves. So there's a very general sort of convergence theorem of sorts that we'll look at in more detail in the next lecture, called the Lax-Wendroff theorem, which says that if we are approximating a conservation law and we use a numerical flux function to define fluxes and then use a method that's in conservation form, so it's conservative, and it's consistent with the correct flux, which means that whatever our numerical flux function is, if we assume it's a three-point method, then the flux at each interface would be based only on the neighboring cells. If that flux function has the property that when we evaluate it with the same state on both the left and the right, it simply reduces to the correct flux for the conservation law. That's what we mean by consistent with the conservation law. Oh, and we also require that this function script f be Lipschitz continuous, so that as q left and q right approach u bar, we should have Lipschitz continuity. Then it turns out that's enough to show that if our numerical method is converging to some function as we refine the grid, then that limiting function must be a weak solution of the conservation law. So if there's any discontinuities in the limit as we refine the grid, those discontinuities must be approximating shocks in the right locations, moving at the right speed. It is a valid weak solution of the differential equation. So again, we'll look at this in more detail next time, but a couple things to point out is that this theorem, as it's stated here, it does not guarantee that we actually have convergence. It just says if you're converging, if you have some numerical approximation and you can somehow show that it is converging to some function as you refine the grid, or you do numerical experiments and you see that as you refine the grid, it's getting closer and closer and closer to something that isn't changing, and you would like to say this must be the right solution of the differential equation because we see numerical convergence to it, then this theorem is saying that yes, indeed, what we seem to be converging to must be a weak solution of the differential equation. But it doesn't say that we will have convergence. For that, again, you need some form of stability typically. So this is like the consistency condition in any sort of numerical analysis of differential equations. You need both consistency with the differential equation you're trying to solve, but also stability so that as you refine the grid, you can show that you're actually converging to something. And then there's another complication here that we've already talked about, and that is that there's not necessarily a unique weak solution. So this theorem isn't saying that we're converging to the weak solution that we want, or even that every sequence of grid resolutions will converge to the same thing. One sequence of grid resolutions might converge to the proper rarefaction wave. Another sequence of grid resolutions might converge to an entropy violating shock. So if we want to also say that we're converging to the physically correct solution, then we also need to show that the limit that we're converging to satisfies some sort of entropy condition. So in this lecture, we'll talk more about what these entropy conditions are and how we can specify an entropy condition that can be used in conjunction with this theorem later to get more stronger results about actually converging to the right solution. And again, just a reminder that if we look at, for example, Berger's equation, in the case where the left state is less than the right state in a Riemann problem, then we would expect the correct solution to be a rarefaction wave that's spreading out like here. Which you can see by if we smeared out the initial data a little bit, then every value is moving with its characteristic speed, and we would see that that would clearly spread out. Or if instead of doing that, we smeared out the differential equation a little bit by replacing 0 here by epsilon times qxx, adding in some viscosity and then letting epsilon go to 0, then you'd also see that as epsilon goes to 0, this is the solution it should be converging to. That's the one we want to find. But there are other weak solutions that satisfy this Rankine-Hugoniot condition and satisfy the differential equation where it's smooth. In this case, it's identically constant everywhere it's smooth, so it certainly satisfies the differential equation. And as long as that discontinuity is moving at a speed that's the average of left and right states, then that is a weak solution, but it's not the right one. And there's infinitely many wrong weak solutions. Here's another one, for example, where things are split up into part of this is propagating as an entropy violating shock wave, and the rest of it's propagating as a proper rarefaction wave, but it's still not entirely the correct weak solution. Okay, so again, the idea of the vanishing viscosity solution, we add in a viscous term with epsilon positive, let epsilon go to 0, and this sort of mimics the sort of viscosity or dissipative terms that are often in the real world that we've ignored in writing down the hyperbolic equation in the first place. But physically, we want to be properly approximating the limit as epsilon goes to 0 of this viscous equation. And in the case of a convex scalar conservation law, then what we find in this limit is that we should get a shock wave only if the characteristics are impinging on the shock from both sides. Otherwise, if we're in a situation where the characteristic speeds are spreading out, then in between here there should be a rarefaction wave instead of a shock wave. So for a scalar convex conservation law, it reduces to something fairly simple, which is often called the lax entropy condition, that discontinuity that's propagating with speed s in the solution of a convex problem is admissible only if the characteristics have this condition where the shock speed, the Rankine-Hugoniot speed, lies in between the characteristic speed on the left and the characteristic speed on the right, so that the waves are impinging on the shock wave. There's a generalization of this to non-convex problems as well, the Olenek entropy condition, which is only slightly more complicated. But for now, we'll be looking at the convex case. So this sort of admissibility condition is often called an entropy condition, and again, the terminology comes from gas dynamics, where if you have a discontinuity in compressible gas dynamics, that's a shock wave that's propagating along, then in a gas, under some in these situations, as long as the flow remains smooth, the entropy of the gas remains conserved, but as a gas molecule goes through a shock wave, the entropy increases. And so entropy can only increase across a shock wave, and so if you have a discontinuity where the entropy function that's defined in terms of the other variables, the pressure and density and so forth, if that's decreasing as it goes through a discontinuity instead of increasing, then that's not physically relevant, and that discontinuity would be violating the physical entropy condition. And so what we call an entropy function mathematically is a function of our solution Q that behaves like this physical entropy for the conservation law that we're studying. It's not generally actually the entropy, but it's called an entropy function if it has the same sort of idea that you can determine whether a discontinuity is admissible or not by whether entropy is increasing or decreasing. But one thing to watch out for is that in physics, the physical entropy can only increase across a shock wave, but the way we define things mathematically, the entropy functions we'll look at have the opposite property, that across an admissible solution, the entropy decreases, and if it's increasing, then that's an entropy violating solution. And the reason for this is that this entropy condition is also often called entropy stability, because if you can show that the entropy is always non-increasing, then that entropy function can also often be used as sort of a norm to say that, in fact, the solution is remaining bounded. Remember that for a conservation law, it may be natural to look at, for example, the one norm of the solution, the integral of the absolute value, and if you can show that that stays bounded, then you may be able to prove something nice about the conservation law or convergence of a numerical method. But you can't necessarily show, just from the fact that a method is conservative, that its one norm is bounded, even though conservation says the integral is conserved, but for the one norm we need the integral of the absolute value. And you can have a conservative method which becomes highly oscillatory with positive and negative values and is still conserving Q, but is not conserving the absolute value of Q, and is going wildly unstable in the one norm, for example. So the entropy function, as we'll see, is a convex function of the solution that can often be used as a norm, and so this entropy condition can also be used as a form of stability. And so mathematically, it's nice to think of the entropy as decreasing for physically relevant solutions so that we have a stable situation. So for a scalar convex problem anyway, also for non-convex problems, but we'll focus on the convex problem here, we'll define an entropy function eta to be just a function that maps Q to some other real number that's a convex function. So I'll assume eta is convex, and now when I say convex, I mean that the second derivative of eta with respect to Q is actually positive. So when we talk about a convex flux in the conservation law, I said we call it convex if F double prime is positive everywhere, or if F double prime is negative everywhere. All that was important was that it had the same sign everywhere. But for the entropy function, it's actually very important that it be positive, because the entropy inequality depends on us choosing it to be positive. If you chose it to be negative, then you'd have entropy increasing across shocks instead of decreasing. So to be able to use the sign of the entropy variation to tell us something useful, we have to assume that it's actually convex with eta double prime positive. And then in addition to this entropy function eta, we also have to find an entropy flux, which we call psi, which goes along with eta. And the idea is that in a smooth solution, eta is conserved and satisfies a conservation law, similar to the one we started out with, where the time derivative of eta plus the x derivative of the flux psi of q is equal to 0. But this only holds where the solution is smooth. And when we have an admissible shock wave, instead of being conserved, the entropy actually decreases. So again, since we're talking about discontinuities, the differential equation as it's written doesn't really make sense at the discontinuity, and so we have to go to a weak form. So what we really mean here by saying that the entropy decreases is that if we look at integrating over a rectangle in x and t, from x1 to x2 and from t1 to t2, then the integral in x at the advanced time up here is not equal to, but is less than or equal to the integral at the original time as modified by the integral of the flux of entropy at the left and right edge. So if we had this conservation law holding everywhere, then this less than or equal to would be equality. But in the case of the entropy, we want equality only where the solution is smooth, and otherwise we want this inequality. So how can we come up with a function that satisfies that sort of thing? Oh, often as shorthand, we might write this as sort of the differential equation eta qt plus psi. That should be psi dx. Psi of qx is less than or equal to 0 rather than equal to 0. But again, when you see that, you should interpret in the weak sense that it's equal to 0 where things are smooth, but where things have discontinuities, then it's this weak form that we mean. And again, this should be an x down here. So how do we find the entropy function and a flux that satisfy that? Well, what we would like to have satisfied is again, this conservative equation in the case where things are smooth. And so if we're assuming it's smooth, then we can write this in a quasi-linear form where we differentiate the time derivative of eta of q is eta prime of q times qt. The x derivative of psi is psi prime of q times qx. So for smooth solutions, we can rewrite it that way. But on the other hand, from our original conservation law, we know that qt is equal to minus f prime of q times qx from the quasi-linear form of the original differential equation if we're assuming things are smooth. And so the qt here we can replace by minus f prime qx, and then if we cancel out the common factor, we're left with psi prime of q is eta prime of q times f prime of q. And so for at least a scalar problem, it's easy to find convex entropies and the corresponding entropy flux. All you have to do is choose any convex function eta of q, whose second derivative is positive, and then once we know eta of q, we can calculate eta prime of q. We already know the flux f from our original equation, compute f prime of q. That gives us the right-hand side, and then we can integrate psi prime in order to get the entropy flux psi. This is much more complicated in the case of systems because if q is a vector with m components, we're still going to choose a scalar entropy eta and entropy flux psi, but in the vector case, the psi prime of q becomes the gradient of psi with respect to all the different variables in q. So that's a vector, and similarly eta prime of q is a vector, and f prime of q is the Jacobian matrix, the m by m Jacobian matrix in the system case. And it's not always clear that a given system even has entropy functions like this. I think for 2x2 systems you can show that you do, but for more than two equations it's not always clear that it does, although for many physical systems you can find entropy functions that have nice properties. But for now we're going to concentrate on the much simpler scalar case. So for example, Berger's equation, in that case, I'm switching the u for Berger's equation, but the flux function is 1/2 u squared, so the derivative f prime of u is just u. We can take eta of u to be any convex function. The simplest one is just u squared. And then from that, from this equation here, multiplying f prime times eta prime, we get 2u squared. That gives us the differential equation for psi prime, and then integrating that gives us finally that psi of u is 2/3 u cubed. So this should look familiar from a few slides ago. Eta is u squared, the conserved quantity is u squared, and the flux is 2/3 u cubed. That's exactly the example we looked at a few slides back, where we were looking at the fact that Berger's equation on the top line here is equivalent to this other conservation law for smooth solutions, but for weak solutions they're not the same. And in general we get a different shock speed for the second equation than for the first. So we use that as an example of why the quasi-linear form wasn't dependable if we're trying to compute shock waves. But now we can take a different viewpoint. We can look at it from the standpoint of entropy functions. We can say that what we're really solving is this top conservation law, but we've defined an entropy u squared and an entropy flux 2/3 u cubed, and we know that that entropy pair is also conserved where solutions are smooth, but in the case of shock waves, that entropy is not going to be behaving the same way as u, and what we saw before is that this Rankine-Hugoniot condition speed for u in Berger's equation is slower than the speed that I'm now calling s star, that we would have to propagate a shock wave in order to conserve entropy. So the fact that the jump discontinuity that we're computing in Berger's equation is traveling too slowly to conserve u squared means that we're going to have a decrease in entropy even though we're conserving u and solving Berger's equation. We'll have a decrease in entropy assuming that there's a shock wave that's propagating with this speed, and assuming that it's the right shock wave. If it's actually should be a rarefaction wave, then it wouldn't be decreasing entropy, it would be increasing entropy. And you can check for this simple case of Berger's equation. We know that in that case, the correct shock wave appears if u left is greater than u right, if we have a shock wave like this in Berger's equation. And then you can compute that the integral of u squared is for a propagating shock wave that's propagating at this speed s. It's going to be moving at a speed where the integral of the entropy is increasing more slowly than the difference in the entropy flux between the right and the left edge. On the other hand, if we have a discontinuity that looks like this, where u left is less than u r, an entropy violating discontinuity that should be a rarefaction wave, then the derivative of the total entropy is increasing too quickly. It's increasing faster than the difference in entropy fluxes would suggest from the integral form of the conservation law for entropy. So just to take another example, let's look at the LWR traffic equations, where the Q is the density of cars between 0 and 1, and f of Q is this quadratic function, some speed limit times Q times 1 minus Q. Here I'm just taking speed limit equal to 1. So we have this flux function, and the quasi-linear form is here. Characteristic speed is 1 minus 2Q. Again, we can take eta of q equals q squared as our entropy function. And again, in this case, the f of q is convex in the sense that f double prime of q is negative everywhere, but we still need eta double prime of q to be positive. So we still want to take a entropy function that has positive second derivative. And then we can go through exactly the same procedure as before to calculate eta prime times f prime, which turns out to be 2q times 1 minus 2q. And then we can, that gives us psi prime, integrate that, and we find that the entropy flux is psi of q is q squared minus 4/3 q cubed in this case. And so again, as in the case of Berger's equation, the physically correct solution, in the case of a shock wave, a physically correct solution, the entropy, q squared, together with the entropy flux, would give us something that's less than or equal to 0 in the weak sense if we integrated around a shock wave. Of course, when q is smooth, then the left-hand side of this equation, if we differentiate this out, this is 2q times qt, and this is 2q times 1 minus 2q qx, and so if we cancel out the two q's, we get this qt plus 1 minus 2q qx, which is exactly the left-hand side of our original conservation law. So where things are smooth, this entropy is again conserved, and we just reduce to the same conservation law. But when there's a discontinuity, then this entropy eta of q equals q squared will be decreasing rather than staying constant. Well, how do we know that decreasing, that less than or equal to 0 is the right sign here? It was for Berger's equation. We could check that by actually looking at what the shock speeds were and checking the two cases where we knew which should be a shock and which should be a rarefaction. But now I've switched to a different flux function that has f double prime negative instead of positive. Is this still the right sign? And how would we show that this is the right sign more generally if I go through this procedure for any f of q? And the way to do that is to, again, go back to the vanishing viscosity solution. What we're really trying to capture is that if we have a discontinuity, it should be the limiting case of what we would get if we solved the viscous equation and let the viscosity go to 0. So what we really mean by that inequality in the conservation law is really this weak form, that when we integrate eta at the advanced time and compare it to the integral at the early time and the fluxes of the entropy at the boundaries, instead of getting an equal sign as we do for the conservation law, we get a less than or equal to, and that's true for any physically correct shock, for any shock that comes as the limiting case of solving this parabolic equation that has smooth solutions with some epsilon positive and letting epsilon go to 0. How do we know that that's the right sign here for any such case? Well, we can actually work it out. So since this parabolic equation has smooth solutions, we can manipulate it by multiplying by eta prime of q epsilon. And if you do that, you get actually the exactly the way that we derived psi, this equation once you multiply by eta prime and use the fact that eta prime times f prime was equal to psi prime. You can rewrite that as the time derivative of eta plus the x derivative of psi. Again, only for smooth solutions, but since we've introduced viscosity, we're only dealing with smooth solutions now, so that's always valid for the viscous equation. But what's different now is instead of 0, we've also got this right-hand side, which we've multiplied by eta prime, and so we get something on the right-hand side here. And now I'm going to rewrite that a little bit, the thing on the right-hand side. We've got eta prime times qxx, and what I've done here is just move that eta prime inside one of those x derivatives. So I introduced an error that gets fixed up here by subtracting off eta double prime times q epsilon x, multiplying the q epsilon x, so we get a q epsilon x squared there. Okay, so what's the point of doing that? Well, sort of twofold. For one thing, the first term here is now an exact x derivative, just like the x derivative of the flux. And so when we put things into this sort of form at the top, the weak form, by integrating over some rectangle, we'll be able to handle that term and turn it into terms that are only on the boundary. But then the other important point is that the term that we introduced by doing that involves, well, it's got a minus sign, but everything else here is positive. Epsilon is positive, eta double prime is positive, and q epsilon squared is positive since it's square. And that's important that all of those terms are positive, and that's what ultimately will give us this less than or equal to sign up here. So just going through the details, again, at the top, this is the equation we were just looking at. But now let's integrate it again over a rectangle in space-time. And so we get the integral at the top boundary, as usual, is the integral at the bottom, modified by the integral in time of the flux at the left and right from integrating this psi term. But then on the right-hand side, we also have an exact x derivative. So when we integrate that, we can also write that as a difference between an integral in time at the left boundary and an integral in time at the right boundary. I guess I've switched the order, but switched the sign. But then there's this final term here, which is not an exact derivative, so there's not much we can do with that except leave it in this form as a double integral in x and t. Okay, but now we use the observations we made on the previous slide. What happens as we let epsilon go to 0? We want to show that we get an inequality coming out of this. So instead of having an equal sign here, we want an inequality involving these first two lines. We want to get rid of the other two lines. Well, this third line, it involves the x derivative of q epsilon. Q epsilon, remember, is the viscous solution, or the solution of the viscous equation. So it's getting sharper and sharper as epsilon goes to 0. It's approaching a shock wave, but it's always smooth. But as it approaches a shock wave, this qx is sort of approaching a delta function. And so we can think of it as sort of being a sharply peaked Gaussian that has a peak amplitude that's blowing up like 1 over epsilon and a width that's decaying similarly. But we're integrating it, and so that ends up giving us, since we're integrating as this delta function goes past the boundary, that ends up giving us something order 1. But then we've also got an epsilon out in front of the integral. And so you can show that this integral actually vanishes as epsilon goes to 0. And so we can just throw away this line altogether when we look at the limit as epsilon goes to 0. Now the last line, on the other hand, has, again, this dq dx, which is blowing up like a delta function, but it's now squared. And so that's blowing up like 1 over epsilon squared. And when we integrate that, it'll still be blowing up like 1 over epsilon. And now the fact that there's an epsilon out in front just means that it is order 1 in the limit. So it doesn't vanish as epsilon goes to 0. It approaches something finite. So we can, as epsilon goes to 0, we can say that this line is going to 0, but this line is approaching something that's finite, potentially. And so we no longer, if we threw that line away, we wouldn't have equality up here. But even though we don't know exactly what it is, we can say something about its sign, because again, epsilon is positive, eta double prime is positive, qx epsilon squared is positive. So no matter what this term is, because of this minus sign out here, it's approaching something that's negative. And so we can throw this line away if we replace the equal sign up here by less than or equal to, because the integral at the advanced time is these other terms minus something positive, so it must be less than or equal to those other terms by themselves. So that finally gives us exactly the result that we want. And there's another form of the entropy condition, just as for the conservation law. You can also look at multiplying the sort of entropy conservation equation by a smooth test function phi, and then integrating by parts. When we did it with the original conservation law, we got something that was equal to 0, and now instead we get something that's greater than or equal to 0. And the condition now is that this should be greater than or equal to 0 for all test functions that are smooth enough that we can differentiate them. So we've moved the derivatives from the solution, or in this case the entropy that is going to be discontinuous at a shock, onto these smooth test functions. But we also in this case impose the condition that the test function should be greater than or equal to 0 everywhere, so that we have a definite sign. And the reason we end up with greater than or equal to 0 over here instead of less than or equal to 0 is because when you integrate by parts, you get a minus sign coming in on these terms. So when we move the derivatives from eta and psi onto phi, we negate things, so we get a greater than or equal to sign there. And again, informally, we might write it in this way, but we always mean one of these weak forms. So finally, let me just go back to this Lax-Wendroff theorem, which I'll talk more about in the next lecture, and just remind you that what we started out with is that if we have a conservative method, and if we observe that it's converging to something as we refine the grid, then if the method was in conservation form, we can at least say that what it's converging to is a weak solution of the conservation law. It doesn't in itself guarantee that it converges to anything, and it doesn't guarantee that it converges to the correct thing. But now that we've introduced these entropy conditions, we can also look at imposing on our finite volume methods a sort of discrete version of the entropy condition we were just looking at. And if you can show that your finite volume method satisfies not only conservation form, but also corresponding version of this entropy condition, then you can show that if you have a solution that's converging to some function as you refine the grid, not only is it a weak solution of the conservation law, but it must actually be the correct entropy satisfying weak solution of the conservation law. So we'll look at that briefly in the next lecture. But also the idea that this entropy can be used as sort of a form of stability is very important. And so not only do we sort of get this entropy condition, but for some numerical methods, you can also show that this entropy stability is also exactly what you need, or at least it's one form of stability that allows you to actually show that the method is converging to not only a weak solution, but the correct weak solution as you refine the grid.